Now I'll work a few examples to show you how this actually functions, how you can use the limit test to determine order of growth. So remember, with limit tests, you really need to have a hypothesis about what the order of growth is. But once you've established that, you can use the limit test to actually check. All right, so let's do this. Let's start with example 1, and we'll ask the same question that I asked a couple videos ago. Does a triangle grow like a line or a square? So example 1, is a triangle, is a triangle, and let's just do it this way, is a triangle big theta of a grid or square, or is a triangle big theta of a line, right? So how's that for some informal math, right? But because you've seen my previous videos, you should know what this means. Right? So literally, what are we asking? We're asking, let's let T of n equal that formula for the number of dots in a triangle, right? So equal 1/2 n times n plus 1. And we're asking, is this big theta of n squared, or is this big theta of n? Right? And we can use the limit test to check both of those possibilities. So here's the setup. What I want to do is I want to say, what is the limit? I want to evaluate. So first, let me back up just a bit. Let me say, let's first look at big theta of n. So first, we'll check big theta of n, right? And we already know it's not going to be big theta of n, so this will be an opportunity to see how that actually works in practice. Right, so what do we do is we'll say, what is the limit as n approaches infinity of T of n, right, where we use this function here, divided by n. So where'd that n come from? Well, it came from the argument of our big theta. Right? So we're asking, in evaluating this limit, we're asking, is T of n big theta of n? Right? Or is it just big O, or is it just big omega? Right? And we'll be able to determine that based on the answer to this. Right, so let me fill this out. So this is equal to, I'm just going to put that in the corner there. So this is equal to the limit as n approaches infinity of 1/2 n plus 1 divided by n. Well, immediately we can see that these n's cancel, right? And so now if we chase this through, I'm going to pull that 1/2 out just to get it out of the way. So I'll say this is 1/2 times the limit as n approaches infinity of n plus 1. And what is this? Well, this clearly is going to infinity, right? So n here is going to infinity, and there's nothing kind of to slow it down. So this just evaluates to infinity, right? So what does this mean? Well, if you think back to the limit test, what does it mean if this thing evaluates to infinity? It means that T of n is big omega of n, right? So this means T of n is big omega of n, but T of n is not big theta of n. So T of n is big omega of n, and T of n is not big theta of n, right? It has a strictly greater order of growth than n, right? So there's our answer. Right? And that's what we expected, right? We didn't expect T of n to grow as slow as n. All right, so now let's do case number 2. So case number 1 was checking is T of n big theta of n. We knew it wasn't going to be, so now let's check what we know is actually going to turn out to be true. Let's check if T of n is big theta of n squared. Big theta of n squared, question mark. How do we do it? Well, we set up the limit. Limit as n approaches infinity of T of n over n squared. So this equals the limit. Don't forget to carry the limits through. The limit as n approaches infinity of 1/2 n times n plus 1 over n squared. So we can immediately, if we want to, we can immediately cancel one of our n's and then pull the 1/2 out. So now this equals 1/2 times the limit as n approaches infinity of n plus 1 over n. Now, there's two basic approaches we can take from here. So one is we could say, look, this is a form where both the top and the bottom of this fraction are going to infinity. So we could use L'Hopital's rule here. Take the derivative of the top and the derivative of the bottom. So actually, why not? Let's actually do that approach. And so I'm going to say this equals, and I'll put in parentheses, L'Hop. Right? So because of L'Hopital's rule, we get this equality. So we have this equals 1/2 times the limit as n approaches infinity of now this fraction of the derivatives. What's the derivative of n plus 1? It's just 1. Simplest power rule there is. What's the derivative of n? It's just 1. And so the limit as n approaches infinity of a function that isn't a function of n is just going to be 1, and so this equals 1/2. Right? So what do we have? We have this is a constant that's greater than 0. So this verifies for us that t of n is in fact big theta of n squared. Okay. Now it's maybe handy to at least one time see a different approach other than L'Hopital's rule. So now let me pick off from here and let me say this equals a different expression, equals the following expression. This equals 1/2, so equals 1/2 times the limit as n approaches infinity of n over n plus 1 over n. Right? So I have n plus 1 divided by n. I can separate that out into two separate fractions, into a sum of fractions, just basic rules of algebra. Now what do I have? I've got n's canceling here. And so if I chase this through, I get 1/2 times the limit as n approaches infinity of 1, right, plus the limit as n approaches infinity of 1 over n, because the sum of the limits is the limit of the sums, right? Limit is a nice additive operation. So what does this equal? Well, now this piece here, this piece is just 1, and this piece is 0. So I end up in the end with exactly the same answer. Right? I end up with 1/2 times 1 plus 0, which is just 1/2. Okay. So I've worked this out in perhaps, at least in painstaking, but maybe in painful detail. For the most part, you don't have to work it out in painful detail if you know you're doing the right stuff. But sometimes it's handy to carry everything through just to make sure that you're not missing anything as you go. But in either case, we end up with this 1/2, which means that we have t of n is big theta of the thing we were checking, right? T of n is big theta of whatever we put in the denominator there.